All right, and here we're back live with the final episode of the 5th season, 5.8. We're solving, I'm changing this word here, not problems, but challenges with exponents and logarithms. A lot of people struggle with the problem solving because they think of it as a problem. I want you to think of it as a challenge, as a puzzle, something to try to figure out. You'll have a lot more success with it. All right, let's go a little bit back here and say, using the formula for the sum of geometric series. Oh, wait. Let's see, what is that formula again? Sum of geometric series was sum of first n equal to T1 or A, depending on which one we do. R to the n minus 1 over R minus 1. So again, this T1 could either be T1 or A. So let's make a list of all the things that we know. Okay, so there's T1, there's R, there's N, there's Sn. And we're looking for the sum. We're trying to determine the sum, so Sn is what we're looking for. That means we need to know the other. R, start with Tn. T1 is your first term. That's 4. R. In order to find the R, you're going to take 4.4 divided by 4, or 4.84 divided by 4.4. Doesn't matter. Any two consecutive, divide the second one divided by the first one. 4.4 divided by 4 gives us 1.1. That's our R value. N, how many terms? Just count them up. 1, 2, 3, 4. There's 5 of them. And then we just plug her straight into the formula. So S of the first 5, S of the first 5 is equal to 4 multiplied by 1.1 to the 5 minus 1. Oh, 1.1 minus 1. Then we just hammer that into the calculator to make sure you got your brackets right. And sum of the first 5 there is 24.4204. Again, check to make sure that you can do this by punching into your calculator yourself. Don't just blindly copy. All right, now we got an investment question. We've talked about these, but we did it graphically. Now we're looking at the algebra behind these questions. So starting with our formula. A equals P, or A original, P1 plus I over N, NT. And we're starting with our principal of 5,000. So we've got A, we've got P, we've got I, we've got N, we've got T. Identify which one are we looking for? We're looking for determine the time. So the time is what we're looking for. Principal amount, that's $5,000 we're starting with. Invested at 3%, 0.03, bring her in as decimal. And N. This one is compounded, there it is, monthly. So N is 12. That means we've got to know A, and it says, when will it double? Double of 5,000, I think that's 10,000 there. Let's plug her in, and we're going to solve for T, but algebraically this time. 10, 1, 2, 3 zeros equals 5,000 times 1 plus 0.03 divided by 12. 2 done 12 T. We're trying to solve for that T. That's an exponent. That means we're going to be using logs here. So the goal is to try to get T by itself. Let's move her here. First thing we want to do, let's divide by that 5,000. So we've got 2. That's the double. That right there, that double is where that 2's coming from. It really does not matter that we start with 5,000 bucks. We could start with $1, and this would be the exact same answer. 1 plus 0.0025 to the 12T. let's clean that up. And we've got an exponent. We're trying to solve for the exponent. We've done those already. Log both sides. Or take it to the log form, but I'm going to just say log both sides. A lot easier to do. So let's log the left side, let's log the right side. So that's where we're stopping that log in there on both sides. Okay. Now we can bring down our exponent in front. Log 2 equals 12t log 1.0025. We're going to divide over 12 and divide over the log. So those two parts are really the coefficient in front of t. The 12 log 1.0025 is the coefficient in front of the t. Let's divide that over to the other side. That means that's gone. We're left with t on that side. T is equal to log of 2 over 12 log 1.0025. That's the exact form there. Punch that into your calculator, and we get approximately 23.1337 years. So a little over 23 years. And it says to the nearest year, so t equals 23 years. And so do a little bit of a check for yourself. What would happen instead if we said annually, or sorry, monthly? What if we compounded semi-annually? How would that change our answer? And would it change it by much? Check that one out. So this next part here is not in your notes book, but it's a really important example to go through. So the idea is take little notes on the side for yourself, but make sure you understand the concept. Safe to college tuition. Lila's parents invested $500 into a savings account on her birthday every year from 13 to 18. 4% compounded annually. How much is she going to have in it? This is why we talked about geometric series, because this is going to be a geometric series. So we know our formula, we've seen it. Our n is 1. It's that. So we've got a simplified version of that formula that we're going to look at. The first deposit at 13 years, on her birthday, she gets $500 put in. That $500 is going to compound for 5 years. It's going to go for 5 years, $500. Now on her 14th birthday, this is the second deposit. It's only going to be able to compound for 4 years. The next deposit, her third deposit on her 15th birthday, is going to compound for only 3 years. Then for 2 years, for 1 year, and that last one on her 18th birthday is not going to be able to compound at all because we want to know when they put in that $500, how much is it. So this is going to be a series, and we're going to be adding those up. So we want to know how much is going to be in that account all the way through. So in this case, we would add all of them up to get our answer. So it would be a little bit easier if we know it's a geometric series if we use the geometric series formula. And that's where this walks in. So here's your formula again. Our n is 6. The reason our n is 6 is if you count 13, 14, 15, 16, 17, 18. That is 6 things. 6 deposits are being made. Your A, or your T1, that's $500. It's going in each time. You're starting with $500. And then it is going up by 1.04 each time. And we're going to do the sum of that. So we just plug it straight into the formula, and we will get the exact same answers if we did all the other, or all 6 of those other terms and add it to So now if we look at each of those deposits, working just like we did with the $500, if we started at the 17th year, Reggie's 17th birthday, that's the same as this n minus 1. It's 1 year before we're done. That deposit's going to be able to go for, and compound for 1 year. The second last one is going to compound for 2 years. We work our way backwards all the way to the first deposit. The third deposit is going to be n minus 3. Second deposit is going to be n minus 2, because that first deposit is going to be able to go for n minus 1 years. And that's really just a reworking of your y equals t1 times r to the n minus 1. That's the formula you learn for geometric sequence, where t1 could be written as a as well. So then we start filling into our sum equation, where your Sn is your amount at the end, where your a value, or t1, is your r, the amount that we're going to be putting in. Your r gets to be 1 plus I. And then we plug her through, and we come up with this new equation. It's not an equation that you have to memorize, but it's an equation that if you're asked to use, you will be given that formula. So when a series of equal investments is made at equal time intervals, and the compounding period for the interest is equal to the time interval for the investments, the amount in dollars, or future value, of these investments can be found with this formula. So it's a formula-based question that uses logs along the way. So it is something that you do have to be able to use. All right, see if you can remember how to do this one here. What's the interest rate per compounding period? If we've got $200, 5%, quarterly investments. All right, let's use that new formula that you just saw. Determine how many monthly investments, that's what we want to know, of $200 you would have to make into an account that pays 6% annual interest compounded monthly if you want $100,000 at the end. Really good type of question for you to budget your money and plan for your future. What do you want to get for an amount of money? What can you afford to put in? How long is it going to take you to get there? Okay, so let's start with our formula. Future value is equal to r times 1 plus I to the n minus 1 over I. Let's fill in what we know. So we know we've got FB, we've got R, we've got I, we've got N. And what we're looking for is how many investments, so we're going to be looking for N, how many. That means we have to know the other ones. Future value, that's what we want to know at the end, 100 grand. R, R is what we're putting in, it's our P, our principal amount. Value. What we're going to regularly put in, our regular payment. I, interest rate, 0.06. And that's now compounded monthly, so we have to divide by 12. That I value, we have to divide by our compound period, which gives you 0.005. Okay, let's plug her in, see what we come up with. So 100,000 equals 200 times 1.1 plus 0.05, 1.005 to the n minus 1 over our I, which is 0.005. All right, let's start getting the n isolated. So let's multiply by 0.005 up and over. So we multiply that up over, we get 500 equals 200 times 1.005 to the n minus 1. Let's divide over the 200 now. Dividing by 200, that gives us 2.5. Well, 1.005 n minus 1. I don't need that bracket there. Let's add over the 1. Add 1 gives us 3.5 equals 1.005 to the n. Woo-wee. Now we're at the point where we say, we've got an exponent, variable, isolated on one side. Hey, let's log both sides. So we now got slap the log there, slap the log there, and give us log of 3.5 equals, bringing that n down, n log 1.005. Hey, divide that log 1.005 over, n is equal to log 3.5. Oh, per log 1.005. Done deal. That is your exact form. But often they're going to say, I want to know what it is in how many numbers. So let's take it to a decimal now. Punch that into your calculator. 251.1784. So now we have to say, do we need 251 or 252? Well, I want $100,000. If I need $100,000, I've got to have more than 251 payments. Because at 251, I'm really close, but I'm not there yet. So your number, you're going to round it out to 252 payments per investment or months. And you can, for yourself, go and say, how many years is that going to be? How long is it going to take you to get 100 grand? The way to do that would be to divide by 12. And that's going to give you 21 years. Yeesh. Not too good. We want to be able to get that money faster. So we got to look for things that are going to help you get more than 4% or 6%, I guess. So more important to most people is to say, how much do I have to pay in order to buy that house, to buy that car? I want to know what I'm going to have to pay. This is called our present value of a loan. So many people borrow money to finance a purchase. A loan is usually repaid to make regular equal payments for a fixed period of time. The amount borrowed is called the present value of the loan. The following formula relates the present value to n equal payments of R dollars. When the interest rate per compounding period is I, the compounding period is equal to the time between payments. First payment is made after a time equal to the compounding period. Blah, 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 blah. Quick thing that you have to know is this is the formula that we can use for it. Again, not something you need to memorize. Will be given to you. You just have to be able to use a formula. So let's buy a car. We're going to use that formula. I get a car, 15 grand. I can only afford to pay $300 a month because that's all I have in my room in my budget. So how long is it going to take me to pay this off if they're charging me 6% interest? Let's do the calculation. Start with your formula. P equals R times 1 minus 1 plus I to the negative n over I. Let's write down on the side, we've got PP, we've got R, we've got I, we've got N. Present value, that's how much you are borrowing, 15 grand. R, you can afford $300 a month. I, 6%, but we're talking about monthly payments. So we got to go 0.06 divided by 12, which again is 0.005. And I want to know how long this is going to be, how many payments I got to make. We're looking for payments. So let's fill it in. 15 equals R 300 times 1 minus 0.1 plus 0.005. Don't forget to divide that interest rate before you plug it in. It's a negative n. Oh, 0.005. I'm going to do something real sneaky. I'm going to multiply up to 0.005 and divide the 300 in one step. I know that's a hard one there. But do two things at once, and we get 0.25 equals 1 minus 1.005 to the negative n. Let's bring over the negative 1.005 to the negative n to one side. Let's bring the 0.25 to the other side, just to try to keep things positive. I don't want to have to deal with it as much. So we've got 1.005 to the negative n equals 0.75. Okay, now we're at that step. We've got an exponent. We're solving an exponential equation. Hey, let's log both sides. Do that, bring down the exponent, negative n log 1.005 equals log 0.75. Let's divide over the log 1.005. 0.75 divided by log 1.005. Hey, let's bring that negative over there too, because I want to know what n is. So n is equal to the negative log 0.75 over, oh, look at that, word in the way, log 1.005. That's the exact form. Punch that into our calculator. 57.6801 ... We can't say 57 months. We've got to round up because we need more than 57. We have to go to the 58th month. And again, if we divide by 12, that'll tell us how many years we have to take. And that gives us 4.83 repeating, oh, that's 3 repeating years, which really means 4 years, and 0.83 repeating, that's 10 months. Oh, wait, that's not too bad to repay a car. Okay, the next part, logarithmic scales. The Richter scale for earthquakes, the decibel scale for sound, and the pH scale for acidity all follow a logarithmic scale. So you're going to have one of those for sure on your home exam. They're going to throw one at you. They're going to have to give you the equation. You don't have to memorize the equation. They will give you the equation. You just have to know how to use it. So Richter went and he developed this formula. I'm not going to read all this for you. It is in your book there. You just need to know how to work it. What you need to know is that one movement up the Richter scale is 10 times intense, more intense. So an earthquake is 6 on the Richter scale. Going to a 7 is 10 times more intense. Or from a 7 to a 9, like they're saying there, or from a 7 to a 9, that's 100 times more intense. And we all know the effect that that March 2011 earthquake had for Japan there. Okay, where we started setting off tsunamis and all that. All right, so we're looking at the Chile 1960 earthquake. Most intense, magnitude of 9.5. The M is your magnitude. The I here is your intensity. And that's the intensity of the earthquake we're looking at right now, where S is the standard earthquake. So we're comparing the two, the intensity compared to a standard intensity. And we want to know how many times more intense is Chile. Let's fill in what we know. We know now, the only thing we're actually told is 9.5. So that's the magnitude. 9.5 equals log of I over S. We need to isolate and solve for I, the intensity, compared to, in terms of the standard. So compared to the S. Well, we know that this is a base 10. We've got a number equal to a log. I told you that before. When we have a number equal to a log, we take it to Expo form to solve. If we had a log equal to a log, then we can drop the log. But number equal to a log, take it to Expo form. That gives us 10 to the 9.5 equals I over S. And let's just multiply the S up and over. So the intensity is 10 to 9.5 times as intense as the standard. That's quite huge. Let's compare that now to the Haiti earthquake. When you look in your book, you see the Haiti earthquake was a 7.0. 7.0. Let's compare the two of them. We've got 10 to the 9.5. That's the intensity to the S. The Haiti earthquake is going to be 10 to the 7 compared to the S. Those S's cancel off. So then we've got now left with 10 to the 9.5 divided by 10 to the 7.0. Hey, like bases, dividing, we're going to subtract the exponents. And you can remember this part right here, that when we're comparing two of them, we can just subtract the two exponents and find the difference as an exponent. We've got 10 to the 2.5. Punching that into your calculator, 10 to the 2.5. That's 316.2277. Over 316 times as intense as that Haiti earthquake that did so much damage. Okay, bringing it together, those two questions. In class, we're not only going to work on the assignment, but I am going to be bringing in some extra questions that use some of the different formulas, especially those three that I outlined at the beginning. So you can see different types of questions as well.